Hi, everybody. Good morning. This is Mrs. Buchanan. We're going to do our first online lesson, and we're going to do it on stoichiometry. I hope everybody's doing well. If you have any questions about this lesson, feel free to email me. Mrs. Book's class may be listening to this lesson also, so she will be able to answer your questions. So let's get started on stoichiometry. So what is stoichiometry? It's the process in which a known amount is converted into a wanted amount. So a German chemist named Jeremias Richter was the person who came up with the word stoichiometry. Stoich means element and metry means measure. So basically what we're doing here is I will give you a known quantity to start with of the reactants, and you will actually convert it to products, or vice versa. You could do it either way. We do this a lot in everyday life, especially when we cook. Cooking is a great example of stoichiometry. When you're trying to make, for example, chocolate chip cookies, and you pull all the stuff out of the pantry, flour, butter, sugar, brown sugar, all those ingredients, your whole goal is to make a known product, and that is the chocolate chip cookie itself. So instead of using food, we're going to use chemicals. So we're going to go back and use a lot of things we've learned over the last year. You're going to review how to balance equations, how to calculate grams to moles. So this is a good review. So how can stoichiometry be used outside of the classroom? Well, chemists use stoichiometry in a lot of things. We use it in the pharmaceutical industry. We use it in the food industry. We also use it, for example, your cars, airbags. There's a known quantity of reactant in the bag, and then when your car gets hit, it actually triggers it to make a certain amount of product. So, for example, you do not want your airbag over inflating because that would be bad. So they have done the calculations to figure out how much product will be produced when that happens. So pharmaceutical industry uses it, and considering the time that we're living in right now, if they're trying to find a vaccine for the virus, they would figure out what their main ingredient is and use that to determine how much product they could use. Food industry uses it because we live in a society where people don't cook for themselves anymore. So companies are figuring out how much of the reactant they have to make a product. So we do use it in everyday life. It just won't be exactly the way it looks for us today. So how do I teach stoichiometry? Well, first, we use what we call a BCA table. And BCA table stands for before, change, and after. If you go on to take AP Chem, this table will be used. It will be used as a BCA table, or when we do equilibrium reactions, we use it as ICE tables. So BCA tables stress the mole-to-mole relationship. So everything that is in the table is converted to moles. So if you're given grams, remember when you go from grams to moles, you divide by the molar mass. So just a little review there. So BCA tables stress the mole-to-mole relationship based on the coefficients in the balanced equation. So for example, it takes 2 moles of hydrogen to react with 1 mole of oxygen, and that will give you 2 moles of water. You can also look at it this. It takes 2 moles of hydrogen to make 2 moles of water, which is basically a 1-to-1 relationship. This balanced equation is what we would call your recipe. Okay, so basically going back to the chocolate chip cookie example, if you turn over the bag of chocolate chips, it has a recipe and it tells you you need 2 cups of flour to 1 cup of butter. Those are all ratios. So ratios are important. BCA tables make it easy for students to determine the limiting reactant. We will talk about limiting reactant, but you will understand that more as we go through this lesson. So here are some steps on how to solve a stoichiometry problem. First, you always must have a balanced chemical equation. If you don't have a balanced chemical equation, you won't have a good understanding, or you'll have the wrong understanding of mole to mole ratios. So make sure you write the equation correctly. So remember how myself and Mrs. Book and the other chemistry teachers have stressed that it's important to know how to write your chemical formulas. Again, if you can't write chemical formulas, it's difficult to balance the chemical equation correctly. So just keep that in mind. Step 2, if you're given grams, you're going to convert it to moles. So remember, you have to divide by the molar mass in order to go from grams to moles. Step 3 is you're going to fill in the BCA table with mole values. And I want to stress that because students sometimes will put the gram value in the BCA table, and it has to be the mole value. And then step 4 is in the final answer. A lot of times the problem will ask you to convert it back to grams. The reason for that is we don't have scales that can measure in moles, so we have to definitely convert it back to grams. So if you go from moles to grams, you have to multiply by the molar mass. So I'm going to give an example problem. Over on the left side of the screen is a problem. It says hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. This is like a really good opportunity for you to write out the chemical reaction, since we haven't done that in a while. And then how many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? So write out the chemical equation. So it says hydrogen sulfide gas, which smells like rotten eggs, burns in air. So remember, if something burns in air, it's reacting with O2. So you would write H2S plus O2 yields SO2 and H2O. So I went ahead and, I guess I'm not very good at PowerPoint, like having it all come in at different stages. So I have it all up here. So 2H2S plus 3O2 yields 2SO2 plus 2H2O. Okay, so remember me going back and after saying how everything that goes in the BCA table has to be moles. If you look over here on the left-hand side, it says how many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide. Okay, so we are given 2.4 moles, so there's no need to convert from grams to moles. It's already given to you. So if you notice here, I have 2.4 moles under H2S. Now, you're wondering, what does this XS mean? Well, if you're not given the other reactant amount, you need to put XS down. And what does that mean? It means that you assume you have more than enough O2. That's why I wrote the letters XS for excess. You have excessive O2, which makes sense. When you're burning something and you're burning it out in the open, you should have plenty of O2. Now, you should also see over here on the product side, I have zeros. So let me explain the before line. The before line is what's in your pantry. So I want to go back to cooking. The balanced equation is your recipe. The before line is what's in your pantry. And right now, what I have in my pantry is 2.4 moles of H2S, and I have excess O2. Now, since I haven't made anything yet, that's why I have zeros on the product side. Zeros will always go on the product side in the before line, okay? So let's talk about how we get the change line. Okay, so we're in step 3 now. So what we're going to do is you're going to use coefficients in the balanced equation to determine the values that go in the change line. So for example, I'm going to use up all 2.4 moles of this. And the reason I'm going to use that up is because the other reactant is in excess. So if you notice, on the reactant side, I have negative signs, and on the product side, I have positive signs. Negative means you're consuming it, you're using it up. The product sign means you're adding it, you're getting more of it. So as I look here, so I'm going to consume all 2.4 moles of H2S. Now, I got to figure out, based on my mole to mole ratio, how many moles of O2 did I actually use? So I'm going to say 2.4 divide by 2 multiply by 3. That's how I ended up with 3.6. So what I want you to do in your calculators right now is I wanted you to take 2.4, divide it by 2, and you're dividing by the mole ratio of 2 H2S, and I want you to multiply it by 3 O2, by the 3 coefficient, and that should give you 3.6. And that's how many moles of O2 you're actually using in the reaction. So, if I look at the product side, the ratio of H2S to SO2 is 2 to 2, which in theory, that's just 1 to 1. So if I take 2.4 moles of my H2S and I divide it by the 2 coefficient in H2S and I multiply it by 2, then I'm going to end up with 2.4. And that's how I got how many moles of H2O. So to get the values in the change line, you need to divide 2.4 by the coefficient you want to get rid of and multiply it by what you want to get. Okay, so now we're going to figure out how to do the after line. And really the after line is just about what you end up with at the end of the reaction when it's all over. So the after line, it's just some basic math. Since I consumed all 2.4 moles in the change line of H2S, 2.4 minus 2.4 is 0. So that's how much I have left over. That's really what the after line is about, is how much do you have left over of your reactants and products. So then I use the 2.4 and I take 2.4, divide by 2, multiply by 3. Again, that's how I got negative 3.6. Now, how did I get excess in the after line? Well, if you have excess minus 3.6, you're still just going to have excess. That's just the math. If you take 2.40 and 2.4 and you add them together, you have 2.4 moles of SO2 produced, and you have 2.4 moles of H2O produced. So it's just some simple addition and subtraction in the after line. The after line, again, gives you the idea of what was used up in the reaction and what was actually made in the reaction. Now, once you're given all the mole values, it's really easy just to go now and convert it back to grams. So I know the problem did not ask you to find grams of O2, but it might be good practice if you see that here you've used 3.6 moles of O2. In order to convert from moles of O2 to grams of O2, you are going to multiply by 32 grams in order to give you the correct answer for that. So that's what this slide is about. If the problem requires you to convert to grams, remember to multiply by the molar mass when converting to grams. So I'm going to stop here for today because I want you to practice. You received an email from me, and the email was about the homework problems that I want you to do in the packet that I gave you before you left. If you were not in school or you have misplaced that, I actually put a copy in Google Classroom for you to go back through and print if you can. If you do not have printing capabilities, then just write the problems out on some notebook paper. If you have questions, you are more than welcome to email me. My office hours are from 9 to 11 in the morning and then 1 to 2 in the afternoon. If you actually have I will be available on my email. I'll be checking it periodically. So if you email me in the evening, there's a good chance that I will respond. Also, I'm looking at setting up Google Meetings, and you'll get an email from me so you can ask me questions about that. So again, I hope everybody's doing well. I look forward to seeing you back in the classroom. Let's hope that by Easter all of this is over and we can come back and we can be in the lab together and do some fun things. Miss you all. Take care of yourselves. And hey, send me a note and let me know how you're doing. Take care. Bye.